All right, so we're simplifying radicals. This is really not loading. It's because the image is so gigantic. Okay, we're going to simplify radicals, which are just square roots for now. We are later going to talk about cube roots and quartic roots. I don't know that that's what they're called. So we said last week that we're trying to identify identical, those words are very similar, pairs of multiplying numbers. The key here being pairs, because we're looking at square roots. For example, the cube root of 8 is 2. That one doesn't look for pairs. That one's looking for 3 things. Right, and so we have 3 2's because it's looking for 3 things. Is there a way for me to, yeah, there we go. So that one's not looking for pairs, but most of the things that we are looking for are going to be pairs, right? So the square root of 9 is 3, and the square root of 16 is 4. We said these things last week. The issue comes when we do things like the square root. I should have sent that as 2 different messages, because now it's not opening as PDF. Oh boy. Failed to send. Amazing. Sorry, it's giving me weird messages because of how that uploaded. There we go. Okay. We'll figure out the picture of the baby later. Okay, so simplifying radicals. So we're going to start, we'll do some of these. I don't want you to have to do all 20. That's weird. Oh, yeah, it only gives you the odd answers. Interesting. All right, so I don't want you to have to do all 20 of these for homework, so we're going to do some of them. The issue when we're taking square roots comes not when the numbers are identical, because I'm sure that we can mostly figure out like the perfect squares. The issue comes with simplifying things that are more complicated. Square root of 343, I don't know what the square root of 343 is, and I don't actually have an idea before I start. I'm pulling this number from the simplifying radicals page. This is number 1 on that PDF. Okay, and it's going to be homework. So I don't know what numbers multiply, and we'll just do our factor tree, but I'm going to guess 3. Actually, I don't think 3 works, but I'm going to guess it anyway because it's got a 3 here, right? So we're just going to guess some numbers. And so we use our calculator to just guess values. 343 divided by 3 is not a whole number, right? Google tells me that it ends in 0.3 repeating. So that is not a number that works. So it's not 3. It's not going to be an even number because it's an odd number. 343 is odd. So we're not going to guess an even number, like 2 or 4. So that leaves 3, 5 for thinking about prime numbers. 5 isn't going to work because it doesn't end in 0 or 5, which means our next number is 7. So I divide 343 by 7, and I get 49. Who knew? So my steps there, my process of elimination was check prime numbers, So that's 2, 3, 5, 7, 11, 13. Check those. Check if it's divisible by those. Okay, so what we're saying here is that 7 times 49 gives us 343. And then this splits into a 7 and a 7, which means I have a pair and I have 1 left over. And so we get this. So the first thing we do is check primes. The second thing we do is pairs. I'm going to say leave the square root. The story that I tell for this is that we have a number in a radical party, in a radical house, right? So this thing. And it's just the multiplication of all the people that, all of the numbers that showed up. So at this party, we had a 7 show up, we had another 7 show up, and we had another 7 show up. And what happens at parties? Well, human beings like to pair up and do things together. And so they leave the party together as one. So the pair leaves the party, and they're not in the house anymore. But this poor 7, all by himself, all by his lonesome, stays in the party, hoping that another person for him shows up, or them. Numbers don't have gender. Or do they? Do they? No, no way. Maybe in Spanish or other romantic languages that genderize words, like German. Does German? Things I don't know about that I think I know about, clearly. Yeah, usually when we're in class, I tell that story, and it's a bit more obvious what I mean, but also not. There's always a reaction. But hopefully it helps you remember how to do it. One year I was telling that story, I had an admin walk in the middle of it, and I was like, well, not stopping now. Okay. So that's 343. Let's do another one. 112. So even numbers are especially easy. Yeah, you ought to look out. Even numbers are especially easy because you just divide by 2 every time till it's not even anymore. So 212 divided by 2, I mean 112, not 212. 112 divided by 2 is 56, which is still divisible by 2. 56 divided by 2. 56 is also divided by other numbers, but that's okay. And then 28 is divisible by 2. And 14 is divisible by 2. And then we're left with 7. I used a calculator to do all those, even though I could have figured them out in my head. I could have figured out 212 divided by 2. I mean 112 divided by 2. I don't know why I see 212. I could have figured out 56 divided by 2, but I used a calculator because it's easy. Now, we're like, well, I have a bunch of pairs. Don't count this one. This is not part of the problem. In my head, I was looking and I was like, oh, weird. No, this is a pair of 2's, and this is a pair of 2's, which means that this is equal to 2 times 2 times the square root of 7. The 7's on its own. It's left over. So that means this is 4 root 7. Okay, 4 root 7. I want to do one more where there's something left over. Yeah, that one. Number 3, 54. Do those look different on the camera? The orange and the red? Like a little bit. Square root of 54. Well, what numbers multiply to bank 54? We just did 2's because it was even. So 2, which means we are left with 27. Is this answer wrong? No. No? Now I'm confused. No, it's not. Okay. Confused myself. 27, which turns into a 3 and a 9, turns into a 3 and a 3. And this example's actually important because we have a pair of 3s, but then there's a 3 that doesn't have a pair and a 2 that doesn't have a pair. So this turns into the pair of 3s on the outside, and then on the inside there's a 3 left and a 2 left, which means this is 3 root 6. So we would leave the one number. Okay, that's simplifying radicals using prime factorization. You do not have to do it this way if you can figure out uh, another way to do it. That's not really what I'm trying to say. If you can figure out that 54 is divided by 9, and then it's 9 times 6, and do the square root of 9 is 3, and we have 6 left over, that's fine. You don't have to go all the way to the prime numbers if you find perfect squares. So like here we found 49. I would just say, oh, 40 square root of 49 is 7, and then we have a 7 left. You don't have to go all the way to the pairs. Okay? So that's simplifying radicals. Do we need that still? Maybe we need that still for a moment. We're looking for prime numbers that multiply. We're looking for pairs because square roots are asking what are pairs of numbers. And we are not writing them as decimals because decimals get rounded and we lose the decimal information. We lose the round. If it's repeating forever and we chop off after the hundredths place or something in decimal terms, well, we've lost what might feel like not a lot of information, but actually it is a lot of information because it goes on for infinity. So it's not a huge value of information, but it is a large quantity of information, even if we even if there's no use for a lot of those decimals, right? At some point in the real world, we just round. Okay, here's what we need to talk about next. Imaginary numbers. Imaginary numbers. I. So, a long time ago, imaginary numbers kind of come with the story because I think the name is awful. The name makes you think, or makes people think, that imaginary numbers are somehow they're not real. And I don't mean real in the math terms where we have the real numbers and the imaginary numbers. It's like a group of numbers, a specific name. I mean like real as in they exist in the world. Imaginary numbers exist and get used in real life all the time. And they have applications and uses, and most of those applications are much higher level than we're able to do because they're electronic in nature or three-dimensional in nature or that kind of thing. So there's physics that use these, real life physics. Most of that physics is electronic based, and so it has to do with current and stuff like that, and not with use imaginary numbers a lot with modeling too, but not with the part of physics that describes object movement. It's like when you get into joules and amps and all those things. So imaginary numbers are real things, and they get used, and they're valuable, and they're important. The reason they're called imaginary numbers is because mathematicians are petty and ridiculous. So when imaginary numbers were discovered, discovered is kind of a weird word when we talk about math, or invented is a weird word. I mean, discovered is what really happens. The reality exists out there. We just haven't conceived of it conceived of it yet or understood it in a way that we write down. And so the first person to talk about quadratics and taking square roots of negatives wrote a paper on it and decided to, this was a thing that should happen and is a valuable piece of information. And then another math person was like, no, that's ridiculous. You cannot take the square root of negative numbers. They're imaginary. He was trying to insult the other person's work by calling them imaginary. And unfortunately, that name just stuck. We just call them imaginary numbers still, which is very frustrating because it doesn't help us learn what they are. And so mathematicians, don't always agree on things. And back when there wasn't Twitter and you could just subtweet people, they would write silly, ridiculous papers and letters about each other. So we define I I is defined as the square root of -1. When we're talking about square roots of negatives, what we do is we use the most basic square root. The square root of 1 is 1. So we use the square root of 1. We use the most basic version and we make it negative. So we have the square root of -1. And this negative means that, or defining I as the square root of -1 means that we can take the negative out of our square roots when we're simplifying and rewrite it as an I. I is not a variable. It's really easy to think, oh, there's a letter, there's a variable. It's a lot more like pi. Pi looks like this. Or we haven't talked about E yet, but E is a number, not a variable. It doesn't change in value. That's the natural number. So it's a lot more like pi in that it's a symbol we use to represent a value instead of writing the value down. Okay, so imaginary numbers are square roots, oh my goodness, of negatives. And the reason that we're doing I in imaginary numbers is because we have quadratics that don't have roots, they have imaginary roots. And so we'll get to that when we talk about quadratic formula later this week. But for now, we're just going to do basic simplifying with I. So we have some things that are true about I. I squared is -1. The reason for this is if we square the square root of something, it just turns into -1, right? So that's what we're saying. The square root of -1 squared is just -1. We can add i's together. So this is treated like a variable, but it is not a variable. It doesn't change in value, but we treat it like one, right? So I plus I is going to be 2i. I divided by I is 1, right? Because it's divided by itself. I times I is this. Now, when we're looking at squaring I or multiplying I by itself, often a thing that will happen in math classes will be like, okay, if I squared is -1, then I cubed is -I because we take the square out. What we're saying here is I squared times I, and so we get -1 times I, which gives us the -I. So you can evaluate things like I to the 34th. Oh, it's even. How many even numbers do we have? That makes a bunch of -1s. And so then we would multiply the -1s out and see if it's positive or negative. I don't really care if you can do that. So once we've talked about imaginary numbers, I think these are all the properties I care about. We're not even really going to use these last two. It's mostly just, okay, if you square it, it's negative. If you add them together, it's like a variable. the next piece is complex numbers. Oh my goodness. I'm just having trouble writing today. I don't know what it is. Complex numbers. Complex numbers. Complex numbers are a combination of a real number and an imaginary number. These are always written a plus bi. So we have the real part and the imaginary part. The real numbers being like integers. Real part, imaginary part. And this is going to be important when we're doing the quadratic formula because we're going to get like some real number and possibly an imaginary number added to it. So this would look something like 2 plus 3i or 4 minus 7i. It's a binomial, except instead of a variable, we have an imaginary piece. This is like 7 square root of -1, 7 times the square root of -1. And then we have this real piece. And they can't be combined because one's imaginary, one has a square root of a negative, and one does not. There's an ant on my paper. So what do I want you to be able to do with these? What do you need to be able to do? Well, you need to be able to simplify a square root. Square root of -27. This would be like what we were doing before, simplifying square roots. And I'm pretty sure that PDF, if I'm looking at it, has a bunch of problems like this. Yep. So you need to be able to simplify a square root. You would do the same things that we have been doing, except first, you can take out the negative, right? So this is the square root of -1 times the square root of 27. Taking out the negative, and this is just I. You can even skip this step. You can even skip that step. Because, right, you can just go straight from the negative to, oh, we have an I, and then we have square root of 27. And so this would be 3 times 9. And so the way we would write our answer is there's a number of ways you could write this. So 3 root 3i. This is maybe the most confusing one because we don't know if I is inside the square root or not. Or you could do 3i root 3. This is probably the most clear way to write it. Those are either of them. We don't put I first. It's like a variable, so we write things like 3x. We write things like 3i, not I3. So either of these, this one you just have to make sure that your square root doesn't go over both numbers. So you need to be able to do stuff like that. The other thing that you need to be able to do is you need to combine complex numbers. This could include multiplying. Paper won't go further up. This could include multiplying. So let's just take these two. 2 plus 3i, and let's add them together. 4 minus 7i. And this is just like adding or subtracting numbers with x's or variables in them, right? So we have the 2 and the 4, those go together. So these two combine to make 6, and then in another color, these two combine 3 minus 7 to be minus 4i. So our answer is 6 minus 4i. I want to show you the multiplication. Nah, won't be on the test. When you multiply these, you would set up like, if we were to multiply them, you'd set up the area. Let's do it. Let's do it. Before we do that, let's finish talking about this. So we're combining the real numbers. So the 2 and the 4 are both real. They can be combined. They're like terms. The 3i and the 7i are also like terms. They cannot be combined together, though. It's just the i's go together and the real numbers go together. And so we simplify whatever we can, and then we leave it as it is. And we always write the real number first and the imaginary number second. So I is always going to be the last thing. Okay. We can also subtract these. If we subtract these, we need to add the negative to everything in the parentheses. Now, let's talk about the multiplication. You're not going to have to do this on the test. In a normal year, we would spend more time on it. I just want to show you. So let's use, where'd my purple marker go? Let's use the same two complex numbers, 2 and 3i, and 4 and negative 7i. And you don't need to know how to do this on the test, but I want you to see it. So 4 times 2 makes an 8. 4 times 3 makes a 12i. 2 times 7 is negative 14i because it's negative. And then this is the complicated part. Normally, when we'd be multiplying, we'd have x's in these two boxes. Because of how we write complex numbers, we write the complex numbers at the end. And so the square is going to happen here. And so we get negative 7 times 3 is negative 21i squared. Well, what happens to I squared? I squared is just negative 1. So this box is really just 21. When we multiply complex numbers, we get another complex number. So we get 8 plus 12i minus 14i plus 21. This becomes positive 21 because the square becomes negative. And so it's negative 21 times negative 1 makes positive 21. And then we just combine everything. So 21 plus 8 is 29 minus 2i. I'm not going to do another example like that. You don't need to be able to do that for a test, but you can multiply them. The order of these notes, a bit weird, just because I found a space to do the multiplication, but other than that, it's completely normal. So we have 8 minutes left of class. That PDF I sent you is homework, so I want you to work on it right now, and I'll be here and I can help you. All the problems? How many are there? 20? You have the answers for half of them, and we did 3 already?
You put it as an assignment or just PDF?
I will put an assignment. I just haven't yet. Brooklyn, yeah. So it's not in your assignments. I will do that right now. Well, that's very strange. Why is there a... And since this is not a test or anything, you should, if you need to, ask for help right now while you're working on that.
So we're going 4 through 20.
Yeah, do I want you to do all of them? Yeah, they're not that hard. right? Because you're just adding and subtracting the numbers. Yeah, so you can do all those. Where did it go? There we go. Yeah, because I did 1, 2, and 3 already, I think. We did those. We're talking about simplifying square roots.